Hey everybody, let's talk about volcanoes. We know that volcanoes are a result of plate boundaries, and just sometimes we'll have subduction, which will create volcanoes. Sometimes we will have plates pulling apart because they're divergent, right? And we'll have lava coming up through that crack that's made. And we'll have things like mid-ocean ridges and seafloor spreading, and that'll create volcanoes. But either way, there are a lot of different types of volcanoes, and they're definitely one of the changes that we see to the Earth's surface as a result of plate tectonics. And so we need to talk about some of the different types of volcanoes, and we need to talk about what causes these volcanoes, because that's really the most important thing, is understanding how these volcanoes are related to plate tectonics and to the surface of the Earth and the changes that we see on the surface of the Earth that have been going on since the Earth's beginning 4.5 billion years ago. So let's look at how volcanoes are related to plate tectonics. We have a map of the world here. Just to orient you, this is North America. This is like the Yukon, Alaska. This is Central America here, and down here is South America. So this would be the Pacific Ocean. And then over here we have the Atlantic Ocean. You can see these jaggedy kind of lines. These are mid-ocean ridges on the ocean floor. And then notice these red dots. This is what I really wanted to show you. The red dots are the volcanoes in these different places. And you'll notice that most of these red dots are on plate boundaries, right? So we know that tectonic plates are always moving. And we know that volcanoes, not always, not 100% of the time, but most of the time, are found near or on the boundaries of these moving plates. Volcanoes are evidence of seafloor spreading, right, along plate boundaries, or of recycled crust due to subduction and rising magma from the mantle as that subduction occurs. So we'll see volcanoes for both reasons, either because the plates are actually pulling apart, or because we're having subduction happen, and so we're seeing those volcanic arcs that form as the magma is boiling from the mantle that is recycled. So like that's an example of what's happening here. It says St. Helens and Mount Lassen, Mount St. Helens and Mount Lassen. These are part of the Cascade Range that is a result of a volcanic arc from the subduction of the Juan de Fuca plate underneath the North American plate. So these red dots line up with plate boundaries, and that's an indication that volcanoes are definitely related to plate tectonics and are a result of moving plates. So let's look at 6 different types of volcanoes. On this page, we have 3 different types. We do have all 6 here in the corner, but we're going to just talk about 3 of them really quickly. We have shield volcanoes, which tend to form really slowly. They have a very gentle slope up. They end up having a very, very large base and can get very, very tall. And in fact, the tallest in the world is Mauna Kea in Hawaii. All of the Hawaiian islands are volcanoes, and they are, most of them dormant, except for the big island of Hawaii and the new island that has popped up to the south of Hawaii, which is an active volcano as well. Mauna Kea is active, and it's actually got snow on it, believe it or not, in Hawaii. And that's because it's so high. It is the biggest mountain in the world because we start measuring at the floor of the ocean, right? And so if you start at the ocean floor and you go up to elevation, Mauna Kea is about 33,947 feet tall, which is bigger than Mount Everest. So we don't feel like the mountain is that big because, we can't see the base of it. It's under the water, but it's definitely bigger than Mount Everest. And that is a shield volcano. Ash or cinder cone volcanoes generally will form from big blobs of lava and ash that are ejected from a single vent. So they don't take years and years to form. In fact, they can form very, very, very quickly. Arcutine, it erupted suddenly in a cornfield in Mexico. This is actually what she looks like today. She's outside of Mexico City in the Mexican Valley, the Mexican Valley. And this volcano's kind of got an interesting story because it just was in a cornfield, and then all of a sudden the guy went out there to farm his cornfield, and there was like a tiny volcano, like overnight. And they can form really quickly and become very big, very fast. They'll have steep edges and they look like a cinder cone, a cone of cinder, which is one of the reasons they're called cinder cone volcanoes. And then we have composite or stratovolcanoes. These form straight up as well, but they take a little bit longer. They are a result of multiple vents. So they have lots of different places or cracks where the lava is coming out. And so they get really big really fast because there's lots of lava coming from lots of different places. And there will be ash and lava, cinder, rocks, even volcanic bombs. And Mount St. Helens, Mount Shasta, which are both in the Cascade Range in Washington State. Actually, Mount Shasta is in California, but Mount St. Helens is in Washington. Anyway, they're part of the Cascade Range. And then Mount Fuji in Japan is also a stratovolcano. So those are three of the types of volcanoes: shield volcanoes, ash or cinder cone volcanoes, and composite or stratovolcanoes. Let's look at the other three. We have fissure volcanoes. So this is what happens when you have basically the separation of boundaries, like they're pulling away from each other, right? So when this happens on the ocean floor, we call this seafloor spreading. But this can actually happen on continental crust, which it does sometimes, not very frequently. But one of the places that's happened is in the Great Rift Valley in Africa. And this is actually what it looks like. It's just this crack that's opening up in the Earth's surface. Now, it's not happening all at once. It's happening kind of slowly. But as it happens, the lava seeps up from below and it lines the inside of the crack with lava. So if you were to look down into this rift, you would see lava rock down in there from the seepage as a result of the spreading that's happening. Now, this Great Rift Valley is dormant. It's not currently an active volcano, but we do have fissure volcanoes in Iceland, and those are active right now. So the Great Rift Valley is a good example of a fissure volcano. Dome volcanoes, we see a lot of these actually in Central America, in Guatemala, and in parts of Africa, sorry, not Africa, Mexico, parts of Mexico. Dome volcanoes end up being like kind of small domes that will form at the base of larger stratovolcanoes. So it's a result of multiple fissures opening up. So we have like a larger stratovolcano here. This is the Santiaguito volcano complex in Guatemala, and this is the larger stratovolcano, and then we have fissures opening up at the base or at the feet of this larger volcano, and we'll have smaller dome volcanoes forming. And so they'll have like little pop-up baby brother volcanoes that are around the larger big volcano, and that is a result of just those different multiple vents. There will be like smaller explosions of gas and ash and sometimes lava, but these are quite active and they don't do a lot of destruction to the area around them. And they'll sometimes be active for a few years at a time, sometimes just a couple of eruptions, and then they're kind of done. So they're probably the least destructive of the volcanoes. I mean, maybe fissure volcanoes, depending on civilizations and where the civilizations are, but that's why people can live near these active volcanoes and feel safe, which happens a lot in places like southern Mexico and Guatemala in Central America, because these volcanoes feel very non-threatening. People are used to living with them. And then finally, caldera volcanoes. Caldera volcanoes is, these are really giant volcanoes. Usually we'll see these, not exclusively, but oftentimes with super volcanoes. Large, huge pockets of magma that are sourcing a volcano that has had a massive, huge eruption, and then the vent will collapse and leave a large depression. So this is the case in Yellowstone. Yellowstone is a caldera volcano. This is actually a map of Yellowstone. So like the yellow line is the boundary of the park, and then if you look carefully, you can see a red line inside the center of the park, which is the Yellowstone caldera. The Yellowstone caldera is quite large. If you've spent a lot of time in Yellowstone, it's like my favorite place on earth, you can actually drive into the caldera and back out of it. And if you don't know what you're looking for, you can miss it. You can actually see the caldera on a piece of cloth. It's a map in my classroom. It's on the wall that is to the goes to the outside of the building. But anyway, it is a red line in the center of the park, and this is where the vent was, and then it collapsed and it sunk downward, so it's a big depression, and you can drive into the caldera and back out of it again, and it's several miles long. You can't even see the whole thing. So Yellowstone is a good example of a caldera volcano. Also Mount Krakatoa, which you may have heard of in Indonesia, and Mount Tambora, also in Indonesia. So these are caldera volcanoes. So let's talk about what volcanoes do or how they work. So we talked about subduction, right? So this is when you have convergent plate boundaries and you have plates running into each other, right? And one of them kind of dives down underneath the other. So we see a couple of different types of volcanoes in these locations. We'll have stratovolcanoes that will form and create island arcs. This is the case in like Tahiti, and also we see this in Tonga. Okay, we can also see subduction near a continental crust, and this creates volcanic arcs on top of the land. So instead of islands, we have mountain ranges, and this is the case with the Cascade Range in Northern California, Oregon, and Washington State because of the Juan de Fuca plate. So we have what's going on is recycled crust. It goes down underneath, and then it heats up, and it pushes the lava up through the crust next to it. So that's a result of subduction. We can also have seafloor spreading, and seafloor spreading creates mid-ocean ridges. It can create fissure volcanoes on continental crust, and we can have activity as a result of that as well. We can also have hotspots. Hotspots form shield volcanoes, and sometimes they can form caldera volcanoes. In fact, Iceland is a shield volcano that is formed as a result of a hotspot, and Yellowstone is a caldera volcano that is formed as a result of a hotspot. Volcanoes that are formed from hotspots are the only type of volcano that are not made from plate tectonics. Hotspots are random. We'll talk more about them in a few minutes. But all the other types of volcanoes that we've just been talking about, those are a result of plate tectonics. So we'll have a magma chamber underneath the crust of the earth, right? It's down in the mantle, and it will heat up for whatever reason, build up, maybe gases, maybe evaporating water, whatever. And that magma will push up and it'll find a weakness in the Earth's crust, and it will find a way to get out. Sometimes we'll have explosions, we'll have bombs, ash clouds, lots of lava flow. Sometimes we'll have little trickles through side vents, but that's pretty much how a volcano works. If you get a minute, this is a super crazy video. It's really fun and interesting. It's about a guy who is a volcanologist, so a scientist that studies volcanoes, and he's actually on the edge of this volcano here, and he's filming with drones. And you can find out if you watch this video how many drones he's lost to that volcano. Anyway, you can find this in your slides in Canvas. Check it out. It's a pretty interesting video. So why do they form? Well, we've talked about subduction and about how that oceanic crust will subduct as it runs into a convergent boundary underneath the thicker, heavier continental crust, and it'll be full of water. And as it goes down into the mantle and starts to melt and be recycled, that water will escape and push upward. And that pushes magma upward as well, because we have hot water, we have hot gases, and those things are going to explode through the crust and erupt and create a volcanic arc. So that's one of the ways that volcanoes will form from subduction. Pretty interesting stuff. We also will have fissures, right? So we can have seafloor spreading, where we have divergent plates. Those plates are pulling apart and exposing part of the mantle, and that mantle is seeping upward, and as it seeps upward, it's erupting, right? Sometimes it'll form big mountains like mid-ocean ridges. Sometimes it will form rift valleys that are on the land. This is when it doesn't happen in the ocean, it happens on top of the land or on the continental crust. And we can see these areas that are volcanic. Sometimes, like I said, it'll form a mountain range like a mid-ocean ridge. Sometimes it's kind of an interesting depression or a valley that has lava down inside of it. So we can see both things happening with fissures. Like I said earlier, volcanoes aren't limited to plate boundaries. Most of them happen on plate boundaries, but sometimes we'll have random volcanoes that occur in areas that are called hotspots. We're not exactly sure what causes hotspots. We consider hotspots as abnormal. They're super hot regions where, for whatever reason, the mantle is under pressure and it rises up through the crust. This is called a mantle plume. This can occur on, near, or far from plate boundaries. And because we don't really understand what causes them, we can't really understand why they happen or what determines when a hotspot is going to happen and when it's not. Hotspots are stationary, they don't move. So any place in the mantle that has a hotspot in it, it's always going to be a hotspot of the mantle. And so as the plates move over the top, we can see evidence of volcanic eruption from history, but that's because the plate is moving on top of the hotspot, and so it's pushing evidence of that volcanic eruption away from the hotspot as the plate moves. So this is why we have like the Hawaiian Island chain. The Hawaiian Island chain is a result of a moving hotspot. We also see volcanic rock here in northern Utah. The large volcanic rock next to the Hedgehog Cage is a volcanic rock I picked up on the edge of the Great Salt Lake. It is a result of the Yellowstone hotspot here at number 44 that once upon a time was underneath this portion of Utah. But because this plate is moving, we have moved south of that hotspot because this plate is moving to the south. And as a result of that, the volcanic activity is now happening in Idaho and Montana and Wyoming instead of here in Utah. The hotspot didn't move, but the plate above it did. So hotspots are pretty interesting, and they're pretty mysterious. This is just an example of the hotspot underneath the Hawaiian Islands, and that this hotspot has stayed in place as the plate has moved to the north. So we see an island chain as a result of that, where the hotspot is holding still, but the plate is moving. And so we see a chain of volcanic eruptions that are evidence of that hotspot having been in those areas previously, not because the hotspot's moved, but because the plate has moved. This is a super cool video on volcanic hotspots. Go to your slides in Canvas and check it out. You'll learn more about hotspots there. Finally, a really cool video about the Iceland hotspot is right here. This is a pretty cool island, and it's currently active as a result of a volcanic plume underneath. So again, go to your slides, check out this video. All of the videos in these slides are really interesting, I think, because they're about volcanoes. And then finally, our very own hotspot. Yellowstone has one of the largest hotspots that exists on the planet. It is a super volcano. It is directly over the top of a very old and very active hotspot. You can check out information about the Yellowstone hotspot here, and you can also watch how the hotspot changes the landscape of Yellowstone from year to year. One of my favorite things about Yellowstone is that it's different every time I go back, and that's because of the dynamic nature of the hotspot and the way it changes the landscape and the park itself as that hotspot gets active and then gets a little snoozy. But we would consider this volcano active, definitely active. Is Yellowstone going to explode? Definitely. And if you want to learn more about when Yellowstone blows and how that's going to affect us 3 hours to the south, check out this video on the Yellowstone hotspot. Don't forget to turn in your guided notes. Have an awesome day.